Okay, so good morning, everyone. So today we are here to revise organic chemistry, which is chapter 15, chapter 16, part 1, which is alkanes, chapter 16, part 2, which is alkenes. All right, so let's get to the heart of it. What does organic chemistry, organic mean? Now, organic means compounds containing carbon. And these compounds containing carbon are commonly found in living things like us, like plants. And that's why it's called organic. All right. Now, the important thing is to know about carbon. Now, carbon is a very unique element simply because if you look at carbon, the electronic configuration of a carbon atom is 2, 4. It has 4 valence electrons. Obviously, 4 valence electrons is not a fully filled outermost shell. Hence, for carbon to achieve a fully filled outermost shell, it needs 4 more electrons. If it needs 4 more electrons, it will share 4 electrons or it will form 4 bonds. So this is the first concept you need to know. For every single carbon atom, it will form 4 bonds. Hence, when you draw an organic molecule out, you need to ensure that it has 4 bonds around the carbon atoms. All right? This is the most important thing to remember when drawing anything that is organic. All right? Now, we're going to jump straight into the reactions themselves today so that we can summarize the reactions. Now, for this WA, we have only learned 2 families or 2 homologous series of organic compounds. The 2 homologous series we have learned so far are alkanes and alkenes. So we will be summarizing them. You may wish to do them side by side so that you can do a comparison of alkanes and alkenes. Okay, so let's begin. So first thing you need to memorize for alkanes is its general formula. So every single homologous series has their own general formula. The general formula includes N. So for example, alkane is CN, then you have H, 2N plus 2. All right. So what is the meaning of N over here in the general formula? The meaning of N in the general formula is the number of carbon. Hence, if I know the number of carbon atoms in that particular alkane, I just sub in that number as N, and I will get its formula out straight away. All right. So alkane CnH2n plus 2. Alkenes CnH2n. So you can immediately see there's a difference in the general formula of alkanes versus alkenes. And this makes sense because different homologous series should have different general formula. On the other hand, if you belong to the same homologous series, then you would have the same general formula. Now, how can this be tested? This can be tested in a very direct way. State the general formula of alkane. State the general formula of alkene. That's the direct testing. Another good way to test you is basically in an MCQ, I could give you different formula. For instance, if I gave you the formula CH4, you will need to know that it's an alkane. How do you know that CH4, the formula, is an alkane? You know that because C1H4 fits the general formula CnH2n plus 2, where n equals to 1. All right. So CH4 fits the alkane general formula. Hence, CH4 is an alkane. Now we could go on like C2H6, C3H8. Basically, it's just different values for N. Okay, I can give you different options and ask you which one is an alkane. So to work it out, you need to figure out, hey, it fits the CnH2n plus 2. Okay, and we need not stop there, all right? Alkanes is a big family. You could have something like C20H42, for instance. It's also an alkane, where N is equals to 20. So we sub in N equals to 20, and that's how you get 42 for the hydrogen. So on the alkene side, we can do the same, but this time around CnH2n. So for example, C2H4. So alkenes are very easy to tell because alkenes have double the number of hydrogen compared to carbon. So C2H4 is an alkene. C3H6, sorry. C3H6 is an alkene. So basically, if the number of hydrogens is double of carbon, then it's an alkene. Okay, so that's how we can test you on general formula by asking you what is the general formula, or in an MCQ, I could ask you which of the options is an alkane or which of the option is an alkene. Okay. Now, the next thing you need to know about alkanes and alkenes is the terminologies. What is the meaning of saturated in organic chemistry? So, alkanes are considered saturated hydrocarbon. So, what is the meaning of saturated? The meaning of saturated is there is no carbon-carbon double bond. You could say that the alkane does not contain any carbon-carbon double bonds. All right. So saturated means no carbon-carbon double bonds, whereas alkenes are unsaturated. So alkenes are the reverse. Alkenes are unsaturated, and you can deduce that this means there is or it contains carbon-carbon double bond. Carbon-carbon double bond is present in the alkene. Okay, so you will need to know definitions like saturated, unsaturated. The next thing you need to know is, of course, what is a hydrocarbon? So this is very crucial. Another definition you need to know. Hydrocarbon means organic compound, but not just any organic compound. It's an organic compound that contains, as the name suggests, hydrogen and carbon atoms only. So the key thing here is that it must only have hydrogen and carbon to be called a hydrocarbon. Okay, so alkanes and alkenes are hydrocarbons because if you look at their general formula, there is only C and H. There is only hydrogen and carbon atoms. Okay, so the word only is very important. So now that we have finished summarizing the basic things that we need to know about alkanes and alkenes, let's go on to look at what is the reaction like. To understand what the reactions are like, you need to first know what on earth do they have that reacts. What is the functional group that reacts in an alkene, for example? So functional group refers to the group that reacts. Alkanes have no functional group. So alkanes do not have a functional group. Alkanes are not particularly reactive. Okay, they do not really have a special bond or a special group of atoms that reacts. Alkenes, though, you need to know the functional group is this. The carbon-carbon double bond for alkene is its functional group. All right. So of course you can draw carbon-carbon double bond, or you must also learn how to spell it out. Okay. All right. So alkenes do have a special functional group, the carbon-carbon double bond. All right. So that summarizes what's the functional group. Now the carbon-carbon double bond in alkenes is actually the reason why it undergoes certain reactions, as we will see shortly. So now we're going to go on to the reactions themselves. Now that we have spoken about functional group, if you have forgotten, this is about alkanes on the left, and this is about alkenes on the right. Okay, so now let's go through the reaction themselves. Now, alkane undergo combustion and substitution. You need to know alkane undergo combustion and substitution. So what is combustion firstly? Combustion means burning. Okay, so for something to burn, it needs oxygen. All right. Now, there are two forms of combustion. If oxygen is excess, there is a lot of oxygen present. That's complete combustion. In complete combustion, only CO2 and H2O are produced. This is very important. You need to know the two products of complete combustion are carbon dioxide and water. On the other hand, If oxygen was a limited supply, that means you are burning the alkane in a limited supply of air. That is incomplete combustion. In incomplete combustion, you do not produce CO2 because CO2 requires a lot more oxygen to produce. You instead produce CO, so carbon monoxide with just one oxygen, and water. So water is still produced. So the only difference really is whether you get CO2 or CO as the product of combustion. And that all depends on how much oxygen did you supply to the alkane. Okay, so you need to be able to name the products of complete combustion and incomplete combustion. You need to know how to make the links that, oh, complete combustion is when oxygen is plentiful in excess, whereas incomplete combustion is when oxygen is in a limited supply. Limited supply of oxygen, limited supply of air. The next thing you need to know is to how to write the equations, and this is where we come in. You need to know the formula. So for example, CH4 plus O2 forms CO2 and H2O. All right. So you need to balance a chemical equation. You cannot just leave the chemical equation as it is. So now if you look at the chemical equation that's on the screen, you realize that it's not balanced. It's not balanced simply because if you were to count the hydrogens, immediately there is a discrepancy on the left and right. There's 4 hydrogens on the left and 2 hydrogens on the right. That's not allowed because you need to ensure the number is the same on both sides. To make sure it's the same, we basically add a 2 in front of the H2O. All right, that will balance out the number of hydrogen atoms. After you finish the hydrogen atoms, the next step is to look at oxygen. All right, oxygen, you got to count. There's 2 on the left, 2 and 2 more on the right. So on the right hand side, there are actually 4 oxygen atoms. Hence, you will need 2 in front of the O2 on the left hand side to ensure the number of oxygen is the same. So this is how you balance an equation for combustion. Now, inside your notes for alkanes as well as alkenes, there is also other equations, obviously, because you have other alkanes and other alkenes. So a good example, C2H6 is the next alkane. Again, I'm just going to do it quickly. Okay, if you have balanced it correctly, you should get this particular answer. So this is for ethane, the next alkane. Now, how do you balance it? Again, the idea is to ensure the number of carbon atoms, the number of hydrogen atoms, and finally the number of oxygen atoms is the same on both sides of the equation. Okay, so you will need to learn how to balance this. And the way to balance it is to start counting. All right, so we're going to do one more example. The next alkane is C3H8 plus O2. Now it's complete combustion, so it forms CO2 and H2O. All right. So what do I mean by counting the number of atoms? So you start with carbon. There's 3 carbons on the left. If there's 3 carbons on the left, you will need to have 3 carbons on the right hand side of the arrow as well. So how do you ensure there's 3 carbons on the right? By putting a 3 in front of the CO2. So we balance the number of carbons by adding numbers in front of CO2 because it contains carbon. The next step is to look at hydrogens. There is 8 hydrogen on the left. There is only 2 hydrogens currently on the right. 8 and 2, what's the relationship? What could I multiply to 2? I know 4 times 2 is 8, so 4 H2O. And lastly, once you have finished carbon with carbon dioxide, hydrogen you balanced with water, H2O. The last step is to balance the oxygen. Here, 3 CO2 means 3 times 2, 6 O. 4 H2O means 4 times O. So I'm sure you know, 6 and 4 together, the sum is 10 oxygens. If there are 10 oxygen atoms, how many O2 do you need to make 10? What times 2 gives you 10? That's the idea. Okay, so the answer is 5. Okay, so you will need to learn how to balance such equations because it's very well tested. And when it's tested, it could very well be 2 marks, 3 marks even. Okay, so you will need to know how to balance such equations for combustion, even for combined science. Okay, so that completes combustion. So what do you need to know from combustion? You need to know there's complete and incomplete combustion. You need to know what are the products formed. You need to know how to balance the equation for complete combustion. You will not be asked to balance the equation for incomplete combustion usually. So you just need to know the complete combustion, how to write the equation. For incomplete combustion, all you need to know is the products formed are different. Okay? So at this stage, we have finished combustion. Okay? So alkanes undergo combustion. The next one is substitution. No, as we have did in class, substitution is a very simple concept. Okay, it's just like in sports. All right, when you're injured, you need a substitute, right? So a substitute means you replace the atom. In this case, you are replacing hydrogen. So in class, we did the example of CH4. So let's today do the example of C2H6. And this is where we revise how to draw again. So first, C2H6 is ethane. Ethane. From the name, you can tell it's an alkane because the name ends in ane. But next, from the name, which starts with eth, you could tell that it has 2 carbons, or N equals to 2. So eth means there's 2 carbons. So let's revise. Meth is 1 carbon. Eth is 2 carbon. Prop is 3 carbons. So you need to know just the first 3. Meth, eth, prop. But I taught you one more, which is bute. The next one is 4 carbons. You just need to know these. All right. Once you have the number of carbons, finding the formula is easy. How do I know it's C2H6? Because I know F means 2. So I sub in 2 into the general formula just now, and that gives me C2H6. The next thing you need to realize is that when you're drawing, you must make sure that every carbon atom has 4 bonds around itself. So you count the number of lines, the number of bonds. So in this case, it's 4 bonds, right? All right. So ethane or any alkane could undergo substitution. The name of the reaction is substitution with chlorine gas. Now, what can it form? So the idea is substitution means I replaced one of the hydrogen atoms with chlorine. So the idea is replacement. All right, so I've replaced one of the H with chlorine in this case. But where did the H go to? Now, the H didn't disappear, obviously. It must have formed something else. And the something else that you must remember is HCl. It's not hydrogen gas, it's HCl gas. All right? There is no hydrogen produced. It's hydrogen chloride, HCl. Okay? So that is substitution in a nutshell. Now, in this substitution, we have replaced one hydrogen only. But must I stop there? Does it necessarily have to stop there? The answer is no. It could go on, right? So in fact, if there is more chlorine present, it could go on to replace more hydrogen atoms, which means you could very well end up with more products than just this one single product. You could end up with this product too, where 2 hydrogens have been replaced or substituted with chlorine. You could also end up with 3 chlorines, 4 chlorines inside the final molecule formed. It all depends on how much chlorine gas you have used. All right. Now, for substitution to happen, you need a special condition, and the special condition is called ultraviolet light. Okay, so you need to know for substitution, it will not happen in the dark. You will need ultraviolet light to give the initial amount of energy for the reaction to begin. Okay, so that's substitution. Okay, which alkanes undergo in the presence of ultraviolet light. Ultraviolet light is the condition for the reaction to happen. So that's substitution. Okay, so just to recap, alkanes undergo combustion, substitution. Okay, so that was alkanes. Now we shall move to the alkenes. Alkenes undergo combustion, similar to alkanes, and addition. So of course, alkenes undergo combustion, addition. Addition is the one that is unique to alkenes. All right. Why addition is present? Addition means you must have a double bond. If without a double bond, it is unable to do addition. So the reason why alkenes can undergo addition is because there is a carbon-carbon double bond present in alkenes. All right. So what is the role of the double bond? So I'm going to skip combustion now because combustion I went through just now under alkanes. The concept is the same. So for alkenes, let's go straight to addition, which requires the double bond. So the first thing you need to know is that addition, it requires the carbon-carbon double bond. If there's no carbon-carbon double bond, it will not undergo addition. All right? Which means that addition is alkene. Only alkenes can do that. All right? So what is addition? The concept is not difficult. This is an alkene. As you can see, there's a carbon-carbon double bond. Generally speaking, if the structure is given to you, please highlight or circle any of these functional groups that you see. That means if I were to see a carbon-carbon double bond, I will highlight it. So as remind myself, there is a carbon-carbon double bond. It's unsaturated. It can undergo addition. All right, so carbon-carbon double bond present. So addition is possible. So what can you add? You could add aqueous bromine. All right, that's an example. So what is formed? Now you need to be familiar with how to draw what's formed. Now the concept of addition basically is the double bond breaks. The double bond has to break. That means at the end, there's no more double bond present. So the double bond breaks. And what happens next? What happens next is to add on to the carbon atoms originally in the double bond. So what are you adding in this case? You're adding Br2. Br2 means two bromines. Bromine, bromine. All right. So importantly, you need to realize the double bond has broken. The product of addition cannot have double bonds. There is no double bond present after you have undergone addition. Okay. So importantly, let's write it down. There is no carbon-carbon double bond in the products. Next, there is only one single product on the right-hand side. So on the right-hand side of the arrow, there should not be this plus HCl, don't have. Because it's addition, it adds to just one thing. So we need not stop at ethene, we could go on. There are other alkenes, right? So for example, the next alkene has 3 carbon atoms. How would you draw that? You need to know 3 carbon atoms. Does it mean that all of them are joined by double bond? The answer is no. In every alkene, there is only one carbon-carbon double bond. That means the 3 carbon atoms will be joined by one single bond and then another double bond. That's it. All right, there's only one carbon-carbon double bond. After which, you need to ensure that every carbon atom has 4 bonds around itself. So you must ensure you count very carefully so that you do not make a mistake. Many students, when they see the empty spaces, they really want to fill something in, but you don't, because carbon forms 4 bonds. Therefore, if the carbon atom already has 4 bonds around itself, we do not fill more stuff in. Just leave it there. Now, if this were to react with aqueous bromine, just like we said just now, what is the structure of the product formed? So again, you highlight the carbon-carbon double bond. You know that addition means double bond breaks. So now we shall redraw. So this was where the double bond was originally, right? Double bond break, and you are going to add stuff to it. In this case, we are adding bromines. And the rest of the molecule remains as it is. So you notice, I've basically just added bromines. I've done nothing to the hydrogens. Okay? So all I did was to break the carbon-carbon double bond and to add the 2 bromines. And do you realize the 2 bromines are on different carbons? Okay? So the 2 bromine atoms, or the 2 atoms which you add, must end up on different carbon atoms, not the same one. Because if they're on the same carbon atom, it's wrong. Because 1 bromine to each carbon atom in the double bond. Okay? Now, this reaction with bromine is called addition of bromine. Addition of bromine is also called bromination, okay, for short. So bromination is a useful test for unsaturation. So this is what we call test for unsaturation. That means if I wanted to see whether something was saturated or unsaturated, we add aqueous bromine. Aqueous bromine can also be called bromine water because you are basically dissolving bromine in water. All right. Now you can add aqueous bromine, but if whatever you are testing is a gas, you could also bubble the gas into aqueous bromine. Okay, so this is the test for unsaturation. If it's unsaturated, remember what's unsaturated? Unsaturated means there is a carbon-carbon double bond, at least one carbon-carbon double bond. If it's unsaturated, the reddish brown aqueous bromine is decolorized. To colorless. So the idea is it's decolorized to colorless because the aqueous bromine underwent addition reaction with the alkene. All right. This is possible because there's a carbon-carbon double bond present. So it undergoes addition. If it undergoes addition, the bromine reacted, the bromine is gone. If the bromine is gone, then the reddish brown color of the Br2 will disappear. So we say that the reddish brown aqueous bromine is decolorized to colorless. And this is because there is a carbon-carbon double bond present. Therefore, there is an addition reaction. How about saturated? Saturated means no carbon-carbon double bond. So for example, alkane. If it was an alkane, there's no carbon-carbon double bond, there's no reaction with aqueous bromine. No addition reaction with aqueous bromine means the reddish brown aqueous bromine will remain the same, which is reddish brown. So it remains reddish brown. Okay, so this is a color change that you will need to remember for unsaturated. Carbon-carbon double bond present and can undergo addition reaction. Okay, now that was bromination, where you add bromine to a carbon-carbon double bond in an alkene. You need to know how to draw, you need to know this is addition reaction, and you need to know how these reactions, color change, could be used to prove that something is unsaturated. We're just going to move on to one last example of a reaction before we talk about other things, which from chapter 15. All right. Now, besides bromine, what else could you add to an alkene? It's still addition, but why must you add Br2 only, right? So how about another addition reaction? So I'm going to quickly draw this alkene. So again, only one carbon-carbon double bond. Only one carbon-carbon double bond. The other one is a single bond between the carbon. And then you make sure that every single carbon has 4 bonds. So this alkene, I suggest you try drawing yourself as practice. All right, so that you don't get confused how to draw the alkenes correctly. Now, you need not add bromine. You could add hydrogen. Hydrogen is a gas though. It's not aqueous. So hydrogen is a gas. All right. Now, this is also addition because it relies on the carbon-carbon double bond. So since it's addition, we already know for addition to take place, it must have carbon-carbon double bond. The carbon-carbon double bond breaks. That means you are left with single bond. All right. After you are left with single bond, you realize, oh, the double bond was present here originally. So now the double bond is gone, it's broken. It now adds 2 more atoms on separate carbon atoms. So just now was Br and Br. So now it's H and H. The rest of the molecule remains unchanged, meaning nothing happened to the existing hydrogen atoms. So what do you notice? If I add hydrogen gas, the double bond breaks, you get one single product on the right. And you realize, hey, the product on the right doesn't have a carbon-carbon double bond. The product on the right is saturated because the double bond is gone. Whereas the original reactant was unsaturated. So this is how you convert something that is unsaturated alkene to a saturated alkane by addition of hydrogen. So addition of hydrogen converts unsaturated to saturated. So just now we added bromine, now we add hydrogen. It's possible as well. Same style, same mechanism of how it works. Now, because it's addition of hydrogen, this reaction is called hydrogenation. Okay, hydrogenation is how you add hydrogen to an alkene to convert it into an alkane. Now, this requires nickel catalyst. And of course, high temperature and pressure. Okay, now hydrogenation is useful because this is used in making margarine. So this reaction, hydrogenation, is used to make margarine from vegetable oil. All right. So vegetable oil is unsaturated. So how then do you convert vegetable oil, which is unsaturated, into margarine, which is more saturated? So the idea is to add hydrogen under high temperature with a nickel catalyst. All right. So far we have gone through combustion. We have gone through substitution under ultraviolet light for alkane. And we have gone through addition of bromine, addition of hydrogen. So together, you have learned 4 different reactions. What must you learn? You need to learn how to draw the products. You need to know the name of each reaction. Who undergoes what reaction? Okay? And this is really a very important bit of organic chem. Once you get this, you will probably get 3/4 of organic chem easily. Okay? So we have spent the last 35 minutes discussing 3/4 of organic chem already, which is the reactions themselves. Now, for the next 15 minutes, let's try to tackle the last 1/4 of organic chem. Okay, so I hope you realize the 3/4 that we have just done will require some revision. If you have taken it down, that's good. You will use this to revise. To revise means you will need to read it repeatedly. It helps also to copy it out again, to draw it out again, so that you get familiar with how to draw the reactants and the products. Drawing is important because we need not ask you for the equation, We could ask you draw the product, draw the structure of the product formed by da, 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 da. All right. So being able to draw is a skill. Okay. Now, finally, we return to the very start of organic chem. Organic compounds containing carbon. So where do we get these organic compounds from? Organic compounds are almost always obtained from fossil fuels. That means your alkanes and alkenes, organic compounds, are obtained originally from fossil fuels. There are basically three types of fossil fuels. A solid, which is coal, which you can burn coal to release energy during winter, for example. You can burn coal to actually generate electricity within a generator and so on. But coal is not very, very environmentally friendly. Okay, it burns generally very dirtily. It produces a lot of carbon monoxide because it's incomplete combustion. All right, so coal is not very good. And then we have crude oil, also known as petroleum. Crude oil, unlike coal, is a liquid. It's a mixture. It's a liquid mixture. So how do you separate crude oil? We separate crude oil using the technique called fractional distillation. So the hydrocarbons or compounds in crude oil are separated by the process called fractional distillation. And this is suitable because the compounds inside crude oil have different boiling points. So the idea behind fractional distillation is always about different boiling points of the substances. Okay? Now, for your syllabus, you don't have to memorize. You don't have to memorize what do you obtain at the end, but you need to know why fractional distillation is useful, why fractional distillation is suitable. Okay? Now, besides this, you should also know something about fractional distillation from Sec 3. You will need a fractionating column. So in the case of crude oil, the fractionating column, okay, I'm just going to draw like very randomly, like this. Okay, so this broadly speaking is a fractionating column, right? Now, at the top of the fractionating column is the lowest boiling point. That means the compound with the lowest boiling point is collected at the top. The lowest boiling point is also the smallest molecule. That means those collected at the top of the fractionating column will be the smallest and have the smallest number of carbon atoms. More carbon atoms, bigger molecule. Bigger molecule, higher boiling point. So right at the bottom is the reverse. The largest alkanes and alkenes will be obtained at the bottom of the fractionating column. Okay, so this is a very quick diagram. Of course, there's more than two fractions. There are more than two fractions. I'm just illustrating to you the trend, which is actually more important to know. The trend in boiling points as we go down the fractionating column, the boiling points increase, the molecular size increases. We're going to come back to this in a short while. All right, so this is fractional distillation of crude oil. And the last one, so we have had coal, which is a solid, crude oil, which is a liquid. The last one is natural gas. Now, natural gas sounds very environmentally friendly, but it is actually also a fossil fuel, just like crude oil. So it contributes to emissions of greenhouse gas, pollution. What you need to know about natural gas is that it's mainly this molecule. Natural gas is about 93 to 94% CH4, and CH4 is methane. Okay, this is a fact that you need to know. Okay, natural gas is mainly methane gas, CH4, which is even worse because methane itself is a greenhouse gas. Even without producing CO2, methane itself is already going to cause climate change and global warming. Okay, so you need to know natural gas is mainly methane. All right, so now that you know all this, what's the use of this? Okay, now we're going to return to crude oil because crude oil is the most plentiful and is what we use commonly on a day-to-day basis. After fractional distillation, you end up with some small molecules, some large molecules. It will be all right if they were the same in properties, but they are not. They are not the same. The size of the molecule has an impact on its properties, which is obvious. So, do you notice the smallest has the lowest boiling point? Okay. Now, this also means it has the lowest viscosity. So the ones with the lowest boiling point has the lowest viscosity. It is the least sticky. It flows very easily. All right. That means the largest molecules at the bottom would have the highest viscosity. That's one. Okay. So viscosity, boiling point, they go hand in hand. All right. Which means we can conclude as the number of carbon atoms increases, the boiling point also go up, the viscosity, also goes up. So viscosity and boiling point will go up as the number of carbon atoms goes up. That's one. All right. Now, there's another property which is very important for organic chem, which is flammability. How easily does it burn, catch fire? We need this because organic compounds are commonly used as fuels in your engine. So it must catch fire in the engine. As it turns out, the smallest compounds have the highest flammability. That means they catch fire the easiest. They burn the cleanest. On the other hand, the larger ones have lower flammability. They do not catch fire easily. It takes a lot of energy for it to even start burning. Which means, as the number of carbon atoms goes up, flammability actually goes down. Okay, so you will need to know this. Flammability is the one that doesn't follow the same trend. In fact, it's the opposite. Flammability goes down as the number of carbon atoms goes up. Which leads us to our final point for today. I want flammability. I want high flammability because I'm going to sell these things as fuels. If I wanted high flammability, I must get the smaller molecules, smaller hydrocarbons. So how then do I convert small hydrocarbons into large hydrocarbons into smaller ones? So the idea is the process is called cracking, is to convert larger hydrocarbons to smaller hydrocarbons. Why is this important? Because this is more flammable. Smaller means more flammable. More flammable means more demand. People want to buy it. People will spend money on it. More demand as fuels. Okay, so the idea is how do I convert a larger hydrocarbon into a smaller hydrocarbon? Okay, and that's really important. So this process is called cracking. It's very easy to tell something that is cracking. All right, so this is an example. I'm just giving an example. Okay, so this is an example of cracking. All right, it's an example. Okay, so I started with a very big hydrocarbon, C20 is big, right? 20 carbon atoms. C20H42, which by the way, if you look at the numbers, this is an alkane. How you know it's an alkane? Because it fits the general formula CnH2n plus 2. All right, if you calculate that. All right, so this is a big alkane. I can crack it, okay, to form C8H18 and 6 molecules of X. So of course, the first question is, may I know what's X? How do you work out X? Again, the idea is a balanced equation. I have 20 carbons, I have 8 over here on the right. That means 6X has 12 carbon atom. How do I get 12? 20 minus 8 equals 12. If 6X has 12 carbon, 1X has 2 carbons. We take 12 divided by 6. Okay, so you must always remember to divide. Okay, if by the coefficient, or else you will not be correct, right? So X has 2 carbons. Next, we move to the hydrogen. 42, 18. I'm sure you can repeat the same analysis. So 6X has 42 minus 18, which is 24 hydrogens. So 1X will therefore have 4 hydrogens. 24 divided by 6 is 4. So putting it together, X is 2 carbon, so C2, 4 hydrogen, H4, C2H4, which, look at the formula, C2H4, the H is double of carbon. If it's just doubled, that means it's an alkene. This is ethene. The name is ethene. The molecular formula is C2H4. All right. How about the structural formula? How would you draw this? So you know our molecular formula is C2H4. The structural formula is you need to draw. How to draw? It's an alkene. It got 2 carbons. Must have a double bond. Right? So you draw the 2 carbon first. Then you draw the functional group, the double bond first. All right? So once I've drawn the carbon-carbon double bond, I'm sure it's an alkene. I just need to think every carbon must have four bonds, right? So one more. So this carbon on the left now has 4 bonds. Do the same on the right, 4 bonds. So this is the structural formula for ethene. All right. Now, finally, after deducing out what is X, what else can we ask you? Of course, we can ask you what is the name of this process. The name of this process is cracking. We can also ask you, why is this important? Oh, it's important because smaller hydrocarbons are more flammable and have a higher demand as fuel. And finally, what are the conditions for cracking? Conditions means what catalyst do you need? The catalyst is aluminium oxide or silicon dioxide catalyst. So aluminium oxide or silicon dioxide speeds up the reaction for cracking to convert the larger hydrocarbons to smaller ones. Okay, and high temperature. The other condition needed is high temperature. If the temperature is at room temperature, it's not gonna work, so it's too slow. All right, you need high temperature. How high is high? The exact number is this: 600 degrees Celsius is the high temperature needed for cracking to take place. So when you learn a reaction, you must learn a name. You need to learn how to draw the products. And finally, you must learn the conditions. So this one is aluminum oxide silicon dioxide catalyst and high temperature of 600 degrees Celsius. Okay, so today we have learned all the reactions. So you have learned combustion, complete combustion, incomplete combustion, substitution of alkane using ultraviolet light. You have learned addition of bromine, addition of hydrogen to alkenes. Finally, we end off with cracking. All right. So ensure you learn all these reactions well. Okay, and that really brings us to the end of today's consultation and summary. Okay, I will leave a bit of time for you to type in your questions so that I can take a look at it. All right, so I'll just stop the recording now, but don't leave yet. Please type in your questions that you wish for me to answer in the Q&A function. All right, thank you.